All right, AP Physics friends. So we just finished the Kirchoff's Laws lab, or at least you did, which is why you're watching this video. I pulled up the lab itself just so you can take a peek at it to make sure we're on the same page. Hopefully everything went well, and I really do hope that before you're watching this, you and your lab partners have taken a chance to answer the what do you notice questions. So you did the series circuit, and you hopefully made some observations, and then you did the parallel circuit, and then again, hopefully answered the what do you notice questions, because we are going to address these two pieces, the very bottom here, based on these two experiments. What general conclusions can you draw about voltage and current? And if you haven't really processed this, then the lab itself is useless. This is not a design and conclusions kind of lab where you're graphing things. It's a learning from doing lab. So if you need to pause right here and talk to your lab mates, that is absolutely fine. I would rather that you have a good handle on what you saw before you watch the video. So do that if you need to. Come back when you're ready, and then we will get started. All right, so hopefully now you're feeling good about that. I want to tell you what I'm hoping that you saw, and that is that in a series circuit, if I draw that circuit, so I've got a battery, I've got a couple of resistors, and I have them in series. If I look at my voltage, I hope what you noticed is that if you measure the voltage across here, I'm going to call that VA. Write that more neatly. VA, because I'm going to call this resistor A. I'll call this resistor B, just not so that we're not confused. This is my voltage B, again, measured across, right? And then I'm going to call this over here my total voltage, because that's the total drop across the battery. If I talk about my voltage total, I hope that you found that the total voltage drop was equal to VA plus VB. That is what you should find if you were measuring things carefully. When talking about current, if we look at the current measured, if you measure it in different places, you could measure it over here. Maybe we'll call this the total. Oops, I need to write that as current. Excuse me, that's embarrassing. The current going through, oops, let me write that as current as well. Hello, total, versus the current going through here, going through B, current B, and then maybe the current going through A, if I measured a current right here. I'm hoping that what you found is that the current total, or the current that goes from the battery or to the battery, is equal to the current that goes into resistor B, and that's the same as the current that goes into resistor A. That is what you should find when you're talking about series circuits, okay? I'm going to go ahead and write down what we should see for parallel as well. And if in any moment of this, what you're seeing is not what matches, not what you're seeing doesn't match what you have observed, then please let me know. Call me over so we can have a conversation, because if that's not what you saw, then we need to make sure that we're understanding the situation completely. So in a parallel circuit, we have two resistors that are wired in parallel. I think that I mentioned this earlier, but for all intents and purposes, the length of wire doesn't matter, because the resistance of wire is nearly zero as compared to the resistance through the resistor. So it doesn't matter how long the wires are. And just to be clear, if these resistors were the same, you would have the same interest of going here versus going here, okay? So just to be clear, those lengths of wire do not matter. All right, so now if we're talking about voltage and the series circuit, we could measure the voltage. Here, I'm gonna go ahead and label this, we'll call them C and D, just so we don't get them confused with our A and B from above. I'm going to measure the voltage across C, VC. And I'm going to measure the voltage across D, VD. And then I'll measure the voltage across the battery, or the voltage total right there. And hopefully what you found when you measured the voltages is that the voltage total in parallel is equal to the voltage across C, which is equal to the voltage across D. Okay, and then if we talk about the current, if we're measuring the current in the whole thing, I'm going to go ahead and put it here, right? That's the current that's coming out of the battery. That's I total. And then I'm going to compare that to the current here. We'll call that IC. Sorry that my notes are a little bit small there. I apologize for that. And there's ID. And hopefully, again, what you found when you were making these measurements was that the total current is actually equal to the current through C plus the current through D. Okay? Again, if these are not what you found in your lab, please pause right now. Let me know. Let's have a conversation to make sure that you are measuring things accurately and that, or maybe there's just a little bit of error. A little bit of error is not a big deal, but we want to get basically these observations. The reason for that, friends, is that these observations lead to two really big rules in circuits, okay? And together they're known as Kirchoff's rules or Kirchoff's laws. And I want to make sure that you really, really understand them. So the first rule has to do with voltage, okay? The first rule is known as the loop rule. Okay, and the loop rule says that the total voltage change must equal 0 around any complete loop of a circuit. Okay, so basically what that means, let's go back to our series circuit here for just a minute. That means that if I have an electron that starts here, it starts with, if it's just one battery, 1.5 volts or 1.5 joules per coulomb of charge, okay? Those electrons have that voltage, and as they fall around this circuit, they need to lose 1.5 volts worth of energy as they go around, okay? They're going to lose some of that when they go across B, and then a little bit more when they go across A. The amount that they lose is dependent on their resistance, but in total, the amount of voltage drop that they lose on A and B has to add up to the total voltage because that's one complete loop, okay? As we talk about, I'm going to go ahead and take that off, just so that I don't get confused later, okay? If we talk about the parallel circuit, the same thing is true. So that means that if I've got that same 1.5 volts of, or charge per coulomb that my electrons have here, when they go down and around, they're only going to go around one loop. And if they only go around one loop, they have to lose all of that energy around just that loop. So all of that energy has to be lost as it goes around C, or all of the energy has to be lost as it goes around D. So that means that it has to lose all of its energy in either C or D, but it doesn't get to lose energy around both. Remember that we said that a parallel circuit is kind of like climbing up a water slide tower, okay? So that's the battery part. Right? You're doing work to raise your potential energy, and then you slide down, but you only slide down one slide or the other, which is going through C or through D, but you don't go through both. So in both of those cases, your total voltage drop has to be 0. So you go up and then you go down. And then if you wanted to do it again, you go up and then you go down. And each time you do that, that's a loop. And each time you do that, you have to conserve energy. The loop rule of Kirchoff's laws is really just a statement of conservation of energy. That's all it is. It's just a restatement of conservation of energy. So that's one of the two Kirchoff's laws. Let's do the other one. So the other one has to do with current. So we're going to just go ahead and take a look at the current stuff. Okay. So the current observations lead to what we call the junction rule. So let's see if we can get my stylus to work here. There we go. So the junction rule says that at any split in paths within a circuit, electrons must go or must follow, let's say, one path or the other. And to be clear, that really means not both. Okay, so what does that mean for a series circuit? Not a whole lot. It just means, because there aren't any splits, it means that all of the electrons that leave that negative terminal are going to follow this path, every single one of them, which means that all of the electrons go through this, all of the electrons go through that, all of the electrons go through that. So that means that the current has to be the same in all of those spots. Okay, when we look at it in terms of the parallel circuit, it's a little bit more interesting. So we can imagine all of that current, here it comes, it's coming out of that negative terminal, right? And it gets to this spot, it gets to this junction. And now the electrons can go one of two ways, but they won't go both ways. That's the point. The electrons either go through, in this case, resistor D, or they go through resistor C, but again, not both. So all of the electrons that are right here can either go through C or D, but not both, which means that the current in C plus the current in D has to equal the total, okay? That is the statement of Kirchoff's junction rule. So junction meaning the place where the two paths diverge, okay? And the junction rule, honestly, friends, is just a restatement of conservation of charge. These two rules, again, were articulated by a physicist named Kirchoff. I don't know any dirt on him. If you want to look some up and let me know, that'd be awesome. But anyway, these two rules govern all circuits. So if you can just keep these two things in mind, and again, they're the basics that we know and love, right? Conservation of energy, conservation of charge. If you can keep those in your brain, life is going to be good. Okay, I'm going to use these rules here just for a minute to help us out combining resistors. So this is kind of bringing it back to everything we've done before and allowing us to analyze circuits that aren't quite as simple as a simple series or simple parallel circuit. So I'm just going to derive those rules with you here real quick, and then we will be done with this video. So I'm just going to write down here rules for resistors. This is one of those things that if you just can kind of keep it in your brain, you will be set. So here we go. We're just going to remind ourselves, we're going to use some rules of ohmic devices here for this derivation, remembering that V is equal to IR. That's one way to write Ohm's law, or you could say that I is equal to V over R. That's my preferred way because the current, again, is dependent on a voltage going through a resistor. Okay, so for a series circuit, we know, because we just saw it in the Kirchoff's law's rules, that VT was equal to VA plus VB. I'm just going to write that down again. The total voltage, come on, silly thing. There we go. The total voltage drop around a series circuit is equal to the voltage across A plus the voltage across B. Okay? Now, we know that V equals IR, so that means that I can say that instead of V in each of these cases, I've got the total current times what we're going to call the equivalent resistance. So the game here is trying to figure out if I didn't have a series circuit, what is the one resistor I could put in to replace that and make it still a circuit? So let me explain that a little bit more. I should have articulated this earlier. I apologize. So let's say that I've got 2 resistors in series. The questions in the rules for resistors are, if this is A and this is B, how can I make a circuit that has just one resistor? What resistance do I need to put here that will be equivalent to having those 2 resistors in series? Okay, so that's what I'm looking for, is that equivalent resistance. How big does it need to be? So again, IT times REQ, I'm just using Ohm's law, is going to be equal to IA times RA plus IB times RB. So all I did here again was just to substitute in IR for every voltage that I had. I'm going to look back up here at what I see for my series circuit. Oh, look at that. I know that all of the currents have to be exactly the same, which means that all of my currents, boop, 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 go away. And indeed, my equivalent resistance for a series circuit is just equal to RA plus RB. So it's just going to be all of those resistors that are lined up in series, you just add them up. This is exactly what we saw with our light bulbs. Again, it wasn't quite exactly the same thing because our light bulbs are non-ohmic, but the resistance increases as you put them in series. Okay, halfway there, one more to do when we have a parallel circuit. Again, my game here is that I've got a circuit with 2 resistors in this time. Okay, and I'll call them maybe C and D just to stay consistent from before. My question is, if I want to replace that set of resistors with one equivalent resistor, how big would it need to be? That's my game. Now I'm going to do a similar thing, a similar thought process here. Instead of starting with my voltage, though, I'm going to start with my current. So I'm going to say that I total must equal IC plus ID. And that, just a friendly reminder, comes right from up here, okay? That was the relationship that I had for my currents in parallel. So down here again, we remember, that I is equal to V over R. So everywhere I see an I, I'm going to change it to a V over R. So here we're going to say that the voltage total divided by the equivalent resistance, because that's again what we're trying to find, is equal to the voltage of C divided by the resistance of C plus the voltage across D, the voltage across D divided by the resistance of D. Okay, so again, I just am substituting in I is equal to V over R, so every I am changing to V over R. We're going to remind ourselves again way up here what we saw from your lab, and that was that the voltages are all the same. And so now, hey, if we have voltages all the same, then the voltages themselves are going to cancel out. That does not just get rid of them because they're all in fraction form, these are going to have to turn to ones, okay? But we can write this now as 1 over REQ is equal to 1 over RC plus 1 over RD. It's a little bit uglier, but it's the same sort of situation. And in this case, again, this is for parallel, okay? If I know the resistances of my resistors in parallel, I can find my equivalent resistance by following this rule. And again, as we said before, if they're in parallel, if I've got 2 resistors and I put them in parallel, my equivalent resistance is actually going to go down because there are more paths and more opportunities for travel. Whew, that was a lot. You've got it. You can do this. Lots of problems to come. Have a great day, you guys.